he has been a true pioneer of adult stem cell plasticity and the anatomy of the human interstitium. Dr. Theise's studies in complexity theory have led to interdisciplinary collaborations in fields such as integrative medicine, consciousness studies, and science-religion dialogue. So with that, I turn the microphone over to our guest today, Dr. Neil Theise. Welcome.
Uh, Thank you very much. You can hear me okay? It's all good? Ah, that was a relief. Okay. I was really delighted. Whoops. No, not ready. When I got this invitation, and both because NIH, um, and but because what it looks like what your group is doing is really interesting, and that it's a really fascinating interdisciplinary mix of people, and that's where the fun stuff happens. So I'm going to throw my fun stuff at you and see whether it's of any use. This is where I live. My office is, well, actually, my office used to be in this building, but as I was just saying, I was on medical leave last year. And while I was away, they moved me to a basement down there somewhere. So that's my new office. And notice the lack of windows. I'm not very happy about this. And what I'm going to talk about is the interstitium stuff. There was some back and forth yesterday, both on Facebook and by email, about what people wanted me to speak about, because I understand that a number of people have gotten my book, which is staring at me over there, on complexity theory and all that stuff that he mentioned in my bio. And but we decided to stay with the focus on this stuff. And if there are enough people who want me to come back and talk about that stuff sometime, I'd be delighted to do that. So, when we published the interstitium stuff, there was this whole business about whether it's a new organ or not, as you probably are aware of. That wasn't in the paper. That sort of came out in talking to our press people, and we were a little bit surprised when it turned out to be the hook for the entire thing. I don't think it's an organ. I think it's a system. And if you want to ask me about that, I think we were wrong, but not in the direction people who were naysayers thought. It's not a tissue. It's not an organ. It's a system. And we can talk about that later if you want. Also, a lot of pushback particularly on Twitter and in posts online in various places. Well, there's already an interstitium. That's nothing new. We've known about interstitia for decades, if not centuries, couple of centuries. And that's also true, but the original title of the paper was A Novel Interstitium. This is an interstitium that had not been well described previously. The two levels of scale of interstitium that had been well described are an intercellular interstitium, where you have cells next to each other that do not have excluding tight junctions. You have spaces between them, and cells that are like that include squamous cells, whether they're lining the skin or the oral cavity or the pharynx, the vagina, the anal canal. Those are all lined by the esophagus. Those are all lined by squamocytes, and they have intercellular interstitial spaces that are very tiny. They're on the order of a micron or so, or a little bit bigger. And then you have the perivascular interstitium, which is what it's usually been called. I prefer calling it a pericapillary interstitium to be a little bit more precise. And this is the interstitial space around the capillaries as they come into tissues. This is the space across which nutrients come into the tissue and waste products are excreted out of the tissue into the bloodstream. And, this is a handful of the things we know these interstitial spaces have been responsible for. Cell nourishment and health, morphogenesis, regeneration, cell function generally. It's important that these spaces be permeable. Liquids and solutes move through them. Cells can move through them theoretically, but at this level of scale, that's not a big deal. And then there are mechanical properties, particularly resistance to compression. And that's because, as you'll see, there's hyaluronic acid in here, and we'll turn to that in a bit. And it's a source of lymph. And that's a primary defining feature of the interstitium, which you'll see why it was important to us soon. So this was the paper, and not a novel, an unrecognized interstitium. So it really wasn't significantly recognized in the allopathic Western medical literature. And that becomes an interesting point too. There are occasional reports that we could find where these spaces were described in one tissue or organ or another going back 60 or 70 years. And we cite most of them, the ones we found when the paper was written, we cite those in the paper. But they sort of weren't they weren't well known. They didn't make any sort of impact, it seemed, after their publication. And in projecting the screen, do you see where Zoom is putting up the faces I'm looking at? I'll move us to there. How's that? Oh, that's better.
Looks good news.
Okay. These are the main collaborators for the paper. And it all started with these two guys who are gastroenterologists in my department at the time. And we brought Becky Wells in for a variety of reasons. And she's been the colleague who I've continued doing the research with in the years since. And I'll explain their contributions. So this was all work. I'm now at NYU, but I used to be at Beth Israel Medical Center, not the one in Boston, the big famous one, the smaller non-academic one down the street on First Avenue here in New York. And I happened to be located within the GI division there, not in the pathology department, because I'm a liver pathologist, and that's my microscope. And the GI division wanted an in-house liver pathologist to look at all their liver biopsies and teach their residents about hepatology. So I was sitting in that office for a long time. David, somewhere in the middle of that, became chief of the GI division. His office was 2 doors down from me. And Petros had been one of our fellows who I had taught and done some research projects before, and now was becoming a junior attending. And these guys really love using special endoscopes. And David is very well connected, so that when new endoscopes are invented or developed or modified, they often come to him to see what can be done with them. And so this had been put on the market. It's a probe-based confocal laser endomicroscope that allows you to do in vivo microscopy. And the way it works is you inject a green fluorescent dye, fluorescein, or Phytse, that gives you extracellular contrast. Within seconds, it disperses through all the fluid compartments of the body. And it absorbs at a very specific spectrum, and it has at that time a fixed focal length of 70 microns. Some are being developed that have adjustable depths of focus, and that's going to become important, but I don't have one of those to play with. And so they were using this clinically. And the idea of this basically is that endoscopists want to replace the pathologists and get all our billings for biopsy diagnosis. They can do it in the living tissue and don't have to share it with us. I mean, let's be honest, that's their real interest. But it turns out to be an interesting research tool. So when you look at the esophagus using this endoscope, and these are pictures the guys gave me, here's the squamous lining of the esophagus, and you see the intercellular spaces I talked about before brightly lit up by the fluorescein within seconds. And so this is a cross-section of the esophagus, 70 microns parallel to the lumen. It's not the typical slide where you're looking at a cross-section of the esophagus. You're looking at a parallel section, parallel to the lumen. And there you have the squamocytes exactly like you expect to see. If you look in the small intestine where the villi are, the lamina propria of the villi fill with Phytse. And that's because we've got capillaries here. And between them, we've got interstitial spaces around the capillaries. So these dark dots are the capillaries, and the spaces between them are the pericapillary or perivascular interstitium of the lamina propria of the villi. Now, everywhere you look in the GI tract from top to bottom, and the genitourinary tract, as a matter of fact, they all look exactly like you would expect to look at them from traditional histology, except in two places. In the human pancreatico-biliary ducts, and the urologists see the same pattern in the urinary bladder, interestingly. And so the guys knocked on my door one day and said, we're seeing something in bile ducts that we don't know how to explain. Can you take a look at it? And so they showed me basically this picture. And we see these black bands, and we see these bright spaces. So I took a look at this and I said, what is this? And I said, well, it's capillaries, isn't it? And they said, no, if it were capillaries, the dark bands would be bright and the spaces between them would be dark. So I wasn't sure what to make of this. I looked in some histology textbooks and didn't see anything that looked like this. I pulled some slides because I get liver resections all the time and we have bile ducts. So I looked at the bile ducts and we see what I've been taught for the bile ducts. There's the simple columnar epithelium of the common bile duct. Pancreatic duct looks the same. And underneath it, you don't have any lamina propria really. You just go into a dense submucosa of dense layered collagen. And you see some capillaries. There's a red blood cell in a capillary. And we see these little tiny white spaces, and these are artifacts. They're basically cracking because the collagen is so stiff that when you try to cut a very thin section with a knife, you get artifactual cracking. So I don't see anything here that goes with this. And that became the big puzzle. We finally devised a thing where I'll do this for now. We arranged for a series of patients, IRB approved, we got consent from the patients, who were getting pancreas resections, Whipple resections, because of cancer in the pancreas. And that means that they get the entire pancreatic duct and the extrahepatic common duct removed when the pancreas is taken out to take out the tumor. And so what Petros did was the patients were put under anesthesia. They were injected with the fluorescein. They put the scope down and they confirmed that they saw this pattern, what they call a reticular pattern, in the living bile duct of these patients who were about to have a Whipple resection. And then they proceeded with the Whipple resection, and Petros met me in the frozen section room, the pathology room where we do immediate diagnoses in the middle of an operation to see if something's cancer or not cancer, that kind of thing. And we opened up the Whipple, opened up the bile duct, and put the scope on the bile duct, and we still saw the same pattern. So we still had this pattern in view. And then we took a section of it, embedded it in material that we use to hold things solidly for making a frozen section. And we confirmed that that was still there. So the fluorescein had not leaked out in this process. We had captured the living tissue looking like this was now this resected tissue still looking like this. And then we put it, I'm missing a slide here. So I'll just have to describe it to you. I'm sorry. So what happened was when we looked at the slide that we made, it looked exactly like this. And this is the picture I'm missing, except the dark bands are glowing bright green under a fluorescent microscope now. And instead of the scope, we're on a microscope because we have a slide of the tissue cut thin. And the spaces between them are dark because whatever fluid was in these spaces has flowed out as we've processed the specimen. And whatever these dark bands are made out of, sorry, I'm also on call for the transplant team, so I have to watch my phone. But this is not them, so never mind. But they're going to keep trying. Let me see if I can mute this. Okay. So, oh, where am I? Um, oh, so the bands are bright green. So the fluorescein, which is a highly charged molecule, is sticking to whatever these bright bands are made of. So that was a clue as to what's going on. And then we took the tissue, reoriented it to make a routine sort of slide. And now, through this processing of freezing the tissue, we see the dark bands. And this is a trichrome stain that stains collagen blue. We see the dark bands and we see the empty spaces. But when we fix the tissue, all of these spaces collapse because the collagen bundles are now sticking together. And so coming back to this slide, we realized that what we had called cracks before, artifacts of the stiffness of the collagen, are actually the collapsed remnants of the pre-existing spaces in the living tissue. So this is kind of cool. The wall of the bile duct is this spongy sort of thing that has fluid in it, but it's kind of the bile duct. So at first, what's the big deal? To give you a sense of scale, this is that picture of a bile duct reticular pattern, and the perivascular interstitium is about this big. So this is giant size compared to this. And you do have to wonder, once we establish that all of these are interconnected, which I'll show you, is whether this is a fractal relationship. No one's done the math yet to determine that. I'm not exactly sure how to do that, but it's an interesting question. A lot of the interstitium people that read the first paper and were sort of not welcoming, shall we say, the problem was that they look at this level of scale and they see this, and they didn't understand that this is at a completely different level of scale. And I was at the microscope with some of them, and they were like, but we see this all the time. And it's like, no, you're looking at this level of scale. And that's also a suggestion that it's a fractal system because it's self-similar across scales. We wanted to know what's going on with these cells. I wanted to know, are they some sort of vein, some sort of artery, some sort of sinusoid? And the way we do that in pathology we identify the lining cells, and we have a bunch of vascular markers we can use, like CD34, D240, which is for lymphatic endothelium, CD31, ERG, our vascular endothelium, Live1 is a lymphatic endothelium. These are other things we use for a variety of reasons. And we got two surprises. First off, there's CD34 and positive and Vimentin positive. Vascular endothelial cells have the same markers, except this is negative for CD31 and ERG, so it's not a regular vascular endothelial cell. The other surprise is that the collagen is not completely lined. About 50% of it appears to be lined with cells on one side, but not on the other side. And this shouldn't happen. It's kind of a dogma that wherever you have extracellular matrix in the body, you have a cell interposed between that extracellular matrix and any fluid that's going by. That's why you have endothelial cells lining the capillaries, for example, and the vascular structures of the body. The only exceptions to that I'm aware of are the sinusoids of the liver and the glomeruli of the kidneys. And those are very specific situations, and it's at the microscopic or nanoscopic level. So this is already strange. But you can see that when you go from frozen, so then we did electron microscopy, because endothelial cells have specific diagnostic features by ultramicroscopy, pinocytotic vesicles, Weibel-Palade bodies, and these cells don't have them. These just look like an ordinary fibroblast-like cell. And here's the collagen bundle. Here's the space between the collagen bundle. And here's the cell on one side, but not on the other side. And so this isn't an endothelial cell. It's of any kind. It seems to be a fibrocyte. And when you fix the tissue, the spaces disappear and you wind up having these parallel arrays. So the bile duct is weird. It has this weird wall, and we didn't exactly know why. But I'm a diagnostic pathologist. I do clinical work, and back at Beth Israel, I did all pathology basically. And so literally over the course of the next few weeks, I got a stomach cancer, I got a colon cancer, and I started noticing that in the submucosa where you have dense collagen, they're all the same cracks I expected to see. But now I understand that these aren't cracks, they're remnants of the living spaces. So I'm thinking, oh, it's not just the bile duct, it's the digestive tract. The digestive tract has this weird kind of sponge-like fluid-filled stroma. And then I got a breast specimen, and they always come with, for breast cancer, mastectomy, and they always come with an ellipse of skin on the top. And looking at the skin, looking at the dermis, they're the same cracks. And when I stained it for CD34 and vimentin, they're the same lining cells. So I realized that if you see this, maybe that's an indication that you've got the same spaces. So I went to David and Petros, and I said, what happens when you put the scope on the skin? And they said, we don't put it on the skin. It's an endoscope. It only goes inside. And I said, well, why don't we put it on the skin and see what happens? And we put it on my skin. This is actually my skin. And it turns out in the skin, you see the same reticular pattern. So it's not just the connective tissue of the digestive tract, it's the connective tissue of the skin, which makes you think it's probably going to be the whole body. And the other import here is that, sorry, I have to plug in my phone, which is allowing my voice. That if you see this, it predicts this, and you don't have to do the living microscopy to know what you have here. And this is what allowed us to really move forward in a more extensive way. And the first paper, we showed the same stuff in the submucosa of the esophagus, the stomach, the small intestine, the colon, the urinary bladder, confirming what their endoscopist what the uroscopist had seen. The bronchial, the submucosa of the bronchial tract, fascia, musculoskeletal fascia. I put this in because for years I've been seeing my yoga teacher was also a Rolfer and cranial sacral worker, and I have a weird collagen defect called Ehlers-Danlos syndrome, and it's collagen 3 that's defective, which is the collagen of the interstitium. So that's exciting. And she was always telling me that she could feel the fluid in the fascia. And I always told her, we're just going to have to agree to disagree on this because there's no fluid in the fascia. I can show you under a microscope. And I showed her pictures like this and said, well, those are cracks. But then I realized, oh my God, she's right. There's fluid in these, but they're expanded and her fingers are sensitive enough that she can actually appreciate them. The connective tissue around arteries and veins, pancreatic ducts, the gallbladder, and there's our skin. So this is what we published in that first paper. We still don't know what the spaces are. And it's not a vascular structure. It's not a venous structure. It's not a lymphatic. It's negative for those markers. It's not a vein or an artery or a vascular sinusoid. So what is it? And what I did was, so basically relying on the definition that the interstitium derives from lymph. And it seemed, based on how the fluorescein distributed, that it's also in the lymphatics. It distributed very quickly. Could this be a pre-lymphatic space? If it is a pre-lymphatic space, then we could define it as a kind of interstitium. And so for this, I turn to my clinical specimens again. This is a colon resection from someone who had a colonoscopy. A malignant polyp was found up here. It was biopsied and taken out and proved to be malignant. And so they have to go back and remove the entire stretch of colon. And to make sure they've removed the right stretch, at the time of endoscopy where the polyp was, they inject India ink and they tattoo the submucosa. And here's the pigment and macrophages. And it sure does look like these macrophages are located in these spaces within the submucosa, right? And then there are some free particles that are floating around too, and we'll come back to that. Well, everyone who does general surgical pathology knows that from here, these macrophages go to the lymph nodes. So by definition, this has to be a pre-lymphatic space. And it pretty much doesn't go anywhere else when you're just doing your routine assessment of the tissues. So therefore, these spaces link to the lymphatics and are by definition an interstitium with the fibroconnective tissue. They're the source of lymph. The interstitial fluid through these spaces is entering the lymphatics, becoming lymph. We can also look at cancers the same way. And so here's the surface of a stomach that has a big invasive cancer invading down into the submucosa. And when you look microscopically at it, you see the tumor cells pushing through these collagen bundles, through these spaces. This is not reactive tissue. It's not being damaged. They're just sort of being separated by the tumor crawling along. And where does that go? It goes to the lymph nodes. And here's metastatic carcinoma of the stomach that has come from that lesion moving through those spaces. Dermal invasion of melanoma. It's well known that melanoma, sometimes it invades straight down into the subcutaneous soft tissues, but often it's found at distant sites along the skin. They're called in-transit metastases. And no one really knows how they get there. People think lymphatics or vascular supply, but the lymphatics and the blood vessels aren't running parallel to the skin. They're running downwards. So how to explain this? So we went and looked at specimens of invasive melanoma, and once again, we see the tumor cells moving through the pre-existing collagen, completely quiet, happy, unbothered. There's no reactive changes to here, even though tumor is moving by. And where does this tumor go? Into the subtending lymph nodes. So we proved that this is a pre-lymphatic space and therefore a form of interstitium, and that's what led to the original publication. All of that is the first publication. Now, Becky is interested in the bile ducts. That's partly why we turned to her. And she's an expert in a disease called biliary atresia, a strange disease that babies, after they're born, they start to lose their bile ducts. And she's sort of the queen of biliary atresia. And she has a mouse model of it and is therefore able to sample tiny bile ducts of mice. And this is Jess and Guri, who did this research. And they were interested in the development of the of this interstitium within the bile duct. And what they showed is day 2 after birth, this is the lumen of the bile duct. It's cellular, the wall is cellular, but there's really not much, but there aren't any spaces. But when you stain for hyaluronic acid, there are very few spaces on day 2, more on day 7, and then the space fills with hyaluronic acid in the adult mouse. And so now we're starting to understand that hyaluronic acid is a potential marker for what's going on in this space. And it's not an immunostain, we're using hyaluronic acid binding protein, which is a naturally occurring molecule in our bodies, and labeling it with peroxidase, and then we can use it to stain tissues. So this is a human portal tract with a bile duct, a vein, and an artery. And this is a human bile duct stained with for hyaluronic acid. So now these white cracks that look empty by all normal stains that we do are seen to not be empty at all. They're filled with hyaluronic acid, staining brown. See, brown. And the spaces now are the unstained collagen bundles. These are all collagen bundles. So we can see the interstitium of the portal tract. And then we were also staining for vimentin and CD34 because we wanted to see the cells lining them. And where these two overlap with this particular, you can get double staining with different colors by light microscopy using this technique. And we've published the use of this. And so you see the navy blue of the endothelium staining positive for vimentin and CD34, but you also find such things in the lining cells of some of these spaces. So now we can see the spaces by light microscopy using hyaluronic acid. And that led us to do this project. Odisei is a junior pathology colleague of mine. And we decided to look at the wall of the skin and the wall of the colon. So make a long story short, this is what the colon looks like from the lumen of the colon. This is the mucosal surface and the mucosal glands. This is the lamina propria of the colon. This is the muscularis mucosae here. which we think of as completely surrounding or underlying the entire mucosal surface. But you can see carefully, if you look on H&E, there are gaps. And sure enough, the hyaluronic acid fills those gaps. So this is the pericapillary interstitium of the lamina propria moving down into the submucosa. And from the submucosa, you move down through the muscularis propria. That's the muscle layer that's responsible for peristalsis. And you can see that that comes all the way down through the serosal surface into the adjacent mesentery. There are no gaps from the surface right beneath the cells lining the colon down through the lamina propria, through the wall of the bowel, into the adjacent mesentery. There are no gaps here. It's one single defined continuous space. We could further support this by using colons that there had been a tattoo for a malignant polyp. And here within these spaces, you see that there are macrophages filled with pigment, but you also see that there are loose particles that aren't in macrophages. And when you look further down, this is into the neurovascular bundle that comes into the colon through the muscularis propria. You see the macrophages, but you see free particles. And down into the mesenteric fascia, the free particles there. So we measured these, or Doug did. This is Doug Allison, a very patient, dutiful resident. We looked at 5 cases that had tattoos like this, 50 from every level. So a massive quantity of particles that he measured, and they go from largest to intermediate to smallest the further down you go, which suggests a mechanical fluid possibility. If you think about a stream with pebbles in it, pebbles will get pushed so far, sand will get pushed further, silt will get pushed further. So maybe this size difference reflects the fluid pressures coming from peristalsis that push things out. But it also shows that there has to be transit of fluid and the material within the fluid from one area to another. The skin, we can show the same thing. And we can, I don't think I have the pictures here of the hyaluronic acid staining, but this is a human tattoo that happened to be biopsied for clinical reasons. These were actually amputation specimens that happened to have tattoos in them. And here you have the spaces between the squamous coming down into the papillary dermis, into the reticular dermis. There are the tattoo pigment-laden macrophages, but here are the loose particles, and you see them up here, and you see them down here in the subcutaneous fascia. This is supposed to theoretically be a boundary, but it's obviously not. And we used colloidal silver. I think I'll save time if you want to ask me about this. It's a really interesting special case, but I'd rather hear your questions. And if you want me to return to this, I will. So here we get hyaluronic acid staining. This is the epidermis to the papillary dermis underlying it. And here, as I mentioned, we have interstitial spaces between the squamous. Whoops. And we see that those are in continuity down into the papillary dermis to the reticular dermis. I already showed you the continuity of the lamina propria through the muscularis mucosae into the submucosa. Here we've got the periarterial adventitia, and that's in continuity with everything around the artery. The same can be seen for all veins that you look at. And this is the perineurium, this is a nerve, and you see continuity of all the spaces within the perineurium with the connective tissue of the organ through which the nerve is passing. We ultimately did, and the implication of this is that every vein coming out of an organ and every artery coming into an organ is ensheathed in fibroconnective tissue, which we call the adventitia, and those have the same fluid-filled hyaluronic acid-rich spaces, and those are in continuity with all those tissues through which they pass. So that's continuity out of the organ. And the same thing for the nerves. Nerves coming in and nerves going out all have the same spaces and continuity with the spaces of the tissues through which they pass. We've now developed this really nice triple stain where brown stains the interstitium. This is a little bit of colon, CD34 and magenta showing the capillaries, and D240 staining the lymphatics. And so fluid comes into a tissue through the capillaries, it moves out into the interstitium, and from there goes into the lymphatics. And here we got lucky because that's the open stoma of the lymphatic. There's another one here. So this stain allows you to see extracranially all the fluid compartments of the body and how they relate to each other anatomically. This is breast tissue, and it turns out that the lobules of the breast, they're equivalent to the lamina propria. This is a pericapillary interstitium, and then it moves out from there into the stroma of the breast, which sometimes has fat in it, but here are the collagen bundles, and you see there's continuity all through there. Here's the nice triple stain. There's an artery, an arteriole, a capillary. That's a little bit of a nerve there. And here's a lymphatic, again with the open mouth. This is how interstitial fluid enters the lymphatics to become lymph. And this is really cool because there is this one type of very common type of breast cancer called lobular carcinoma, where cells line up single file in the breast when they invade, and no one's ever been able to explain why they do that. But now it's clear why they do that. They're moving through the interstitial spaces. The collagen bundles are undisturbed as the tumor cells march through. And here we got really lucky, and here are the tumor cells entering into a lymphatic. Two lymphatics, actually. So this is how this tumor spreads to the lymph nodes. We're looking at other organs. This is the pancreas. Up here is the duodenum. That's the common bile duct coming through the duodenum. These are Brunner's glands, which are the glands that are below the submucosa, below the mucosal surface in the duodenum. And you see the hyaluronic acid moving through those spaces. And you see that there are no gaps as it moves through the wall of the duodenum down in through the muscularis propria into the pancreas. And here are some pancreas slides. Here's pancreas that has interstitial spaces between its glands, but those are in continuity with the interstitial spaces between the adipocytes of the peripancreatic soft tissue. This is Sirius red showing collagen and how there's this intimate relationship, a bilayered relationship between collagen and hyaluronic acid throughout all these structures. This is the pancreatic duct, and here's the submucosa of the pancreatic duct, same thing. And here are the lymphatics. That might be an open mouth of a lymphatic there. Here are the islets of the pancreas, and they don't have interstitial fluid between these cells, but around the acini of the pancreas. And these are the capillaries that feed and come out of the islets. And you see that there's a pericapillary interstitium here. This is where insulin, for example, goes from the islets through the body. And here we've got vessels where the adventitia of the artery is also, there's continuity with the spaces. And here we've got nerves in the pancreas with continuity within the nerve, around the nerve, into the pancreatic interstitial spaces. So this is all one single interconnected space. This is a normal kidney. This is hyaluronic acid staining for a normal kidney. No separation, all in continuity, including all its vessels and all its nerves. There's a renal artery with its adventitia. So we have looked at or are looking at and preparing the papers for the liver, all components of the luminal GI tract from esophagus all the way down to the anal canal. The lung, we've already submitted. The heart is really interesting, and if you want to ask me about that, there's some very cool stuff there that's a bit of a surprise. We've done the entire female genitourinary tract. We're looking at skin from the surface of the skin down to the periosteum, and the guy working on this is an osteopath, and so the osteopathic community were sort of up in arms about how they knew about this space. Why are we saying it's new? And they did know. And that's an interesting story as well. But now he's going to document the actual anatomy that they've never been able to do. And I've written a number of papers. It's hard to study in tissue sections, but a number of papers with the Alzheimer's group at Cornell, and they believe that these are the routes for lymphatic drainage out of the cranium and might be important for how Alzheimer's and other degenerative diseases might be functioning. So I'll finish with this list of things that we're thinking about, because it's just, where do you go? The fiber connective tissue is a body-wide network that is comprised of layers that are more stiff, the collagen, or what people generally refer to as fascia, and less stiff, mostly hyaluronic acid, the interstitium. And so I'm working on a fairly high-level committee for fascia nomenclature, and what we're leaning towards is the fascia is a system, and what I would be calling the interstitium is the fascial interstitium. That might be a way we'll go. It's defined as the interface between two domains, the stiff and the less stiff, the more fluid, the fascia and its interstitium, two domains which allows for modulation of shear stress at the microscopic and macroscopic scales. And that would be the definition of what the system does, the way every system in the body has a single defining statement, even though they all do many things. The hyaluronic acid containing domains are water holding and allow for free flow of water and small molecule solutes. The HA may buffer or filter movement of biomolecules based on size and charge. We know it's filtering based on size because we see that with the tattoo pigment, but HA is highly charged. And so we can imagine there's some control here of cytokines and chemokines and growth factors, for example, depending on size and charge. Reductions and changes to HA composition with age, we lose it as we get older. It becomes forms that don't hold as much water. Those are likely to play roles in tissue injury and dysfunction that are associated with increasing age. The resident cell populations of the interstitium include these fibroblast-like cells. There are many types here. If we try and look more closely, there's a large literature on this. These may all have lineage relationships, or some of them may have. It's not entirely clear. Some of them have been shown to be lipogenic precursors, so that's why there's often adipocytes. And the other resident cells of the immune system are pretty much just macrophages and mast cells. And this is particularly interesting to me because people with Ehlers-Danlos syndrome, that collagen defect I mentioned I have, which is a collagen 3 defect, those are the collagen bundles that structure the interstitial spaces. And that's where the mast cells sit. And many people with Ehlers-Danlos syndrome have dysfunctional mast cells. So there's something interesting going on there. There aren't a lot of lymphocytes in normal tissues, but obviously when you get disease, injury, then they're flooding through. So this is a pathway for cells to move, for cellular trafficking. And the interstitium serves as conduits. Peter Friedel is a cancer researcher who was intuiting that these spaces must exist, but he hadn't shown where they were years ago. And this is how a lot of tumors spread and how infections spread, how you get a Staph aureus infection that turns into flesh-eating disease and then suddenly gives you sepsis. It's moving through this space. And when you look at the bacteria that are able to cause necrotizing fasciitis, flesh-eating disease, 80% of them produce hyaluronidase. So they're able to chew up the hyaluronic acid and go through the path. Another thing I forgot to put on here is that Becky's done some work on the collagen bundles as a fibrous network through the body. And that has to do with force transmission through the body. And there are some interesting things going on there. It's also piezoelectric. I forgot to put that on. And finally, the proximity of the interstitium to the skin's stratum corneum. You saw how you've got a few flakes at the top, and then you've got the interstitial spaces between the squamocytes. Those flakes are where the bacteria of the microbiome sit. So this is a direct route into interstitial spaces for microbiome communication that people haven't really considered when they're talking about microbiome. This is the crowd of people who have contributed so far. I'm going to finish up with a little exercise because I've thrown a lot of information at you, but what does the interstitium actually look like? So I'd ask you to sort of sit up straight, close your eyes for a moment and take a few deep breaths and just try to feel your body as an experience of your body. Now open your eyes and consider that the entire cardiovascular tree is ensheathed in connective tissue, which contains hyaluronic acid-filled interstitial spaces. All of that's in continuity. Now picture the central and the peripheral nervous systems, all covered by connective tissue with interstitial spaces. Interweave these in your mind. Now take all the connective tissue covering and interior layers of all the visceral organs and fit that all together. Now add on the musculoskeletal fascia around all the bones, all the skeletal muscles of the body. And then add the dermis. That's the interstitium. It's a very complicated network that goes everywhere. And it's probably, as I said, a fractal network. One last tidbit, it's estimated, this isn't our work, this is a standard number out there in the literature, that the interstitium represents 24% of the fluid volume of the body. That's 4 times the size of the cardiovascular system. So we suggest that there's a body-wide network of fluid-filled interstitial spaces with significant implications for molecular signaling, cell trafficking, and the spread of malignant and infectious disease. Thank you for your attention.
Thank you, Neil. That was just a wonderful presentation. And we've got a number of questions that you've seen, and I'll go through with you in the chat here. But if I could, as the moderator, start you off with just one. And that is, you alluded to, that different groups have been saying that, oh, we've known this for centuries, or
Yeah.
different clinical groups. What's the general, these numbers of knowledge translation takes anywhere from 17 to 50 years or things. How's been your experience of this information making it into, say, school curriculums and just into normal everyday knowledge about the human body?
Yeah. It takes time. The fact that a year ago, Becky and I were invited to an NIH meeting from NIDDK for the kidney, and it just happened to be kidney because the people doing it were kidney people on the interstitium. It was a day and a half global meeting of invited speakers from all sorts of different fields to discuss the interstitium, with Becky and I each leading off with a talk. And there was no pushback in the room. There was just interested discussion about how to study these, what's the dynamics. Fascia world, the osteopaths, craniosacral workers, fascia scientists, that's its own community out there. And they were very angry because they said, well, we've known this stuff for 60 or 70 years. And it's true, they've been talking about it and writing about it, but not in peer-reviewed papers that are widely seen. And at first I thought, well, that's, they should have been publishing elsewhere. But then I realized, no, they weren't allowed to publish elsewhere. The allopathic community didn't really want to hear about this because when you look under the microscope, there are no spaces there, just the way I thought those were cracks. I was in Japan where I consulted because of liver pathology, and they wanted to hear about this. And I gave a talk there the year after the paper came out. And there was a hepatologist who also happened to be their national director for the Institute for Traditional Chinese Medicine. So he got the first question. And he asked me kind of the same thing. How are people responding to this? And I said, well, at first people were really angry because this wasn't new to them. They've been known about it for 60 or 70 years. And he laughed and he said, yes, and we've known about it for 4,000. I now have a network of people I'm speaking to, collaborators, in all these different fields who are sort of looking to this anatomy as a way of explaining, I want to get the, I'm looking at people now. Hi, everybody. The anatomy seems to be a way for people to communicate across language barriers, like the specialty language of their disciplines, not just what their native language is. and find ways to talk to each other and interact and collaborate with each other. And that's, I think, one of it's forming an intellectual interstitium, if you will, which is very exciting.
So Neil, with that, we have a number of questions here about pathology. And of course, you mentioned malignancies and the movement of cancer cells. But in terms of chronic disease or age-related changes or degenerative changes, can you make any comments about that related to either hyaluronic acid or other components of the interstitium?
Yeah, we know that hyaluronic acid depletes as we age, and we know that there are uh, long chain branching and short chain branching, short branch. You know what I'm saying. So there's different forms of HA, how it aggregates, and they all have different water holding capacities. This is why we wrinkle. The dermis is losing hyaluronic acid and its water holding capacity as a result. And so there's less fluid to plump you up. This is why there are all these cosmetics and procedures for putting in hyaluronic acid. The problem is hyaluronic acid doesn't absorb through the skin, so that don't work. I don't know much about where the HA comes from. It's something I keep meaning to find someone to work with, because this is going to be its own specialized thing. I see someone asked, is there some way to augment it or supplement it as we age? That's a multi-billion-dollar industry if we can figure that out. And that's talking only about half the population. So I'm not sure, but obviously there's something intriguing going on there. And I suspect, if I'm right about the buffering capacity of the HA in a healthy interstitium, that, when you look at why do you get a mosquito bite, the inflammatory signaling molecules don't go far. And the explanation for why they don't go far is that they actually diffuse out. And as they move out distance-wise, they become so few in number, the density of them, that they're no longer having a physiologic effect. So a mosquito bite is bounded. But another possibility is that the hyaluronic acid, which is where the mosquito bite is happening, it's in the dermis, is that actually keeping cytokines and chemokines that are important for the inflammatory response on site, and keeping them at a higher concentration, and also preventing a systemic overflow. And that makes me think, well, when you're older, one of the ways people talk about aging is a systemic hyperinflammatory syndrome. Is it because your HA is breaking down and you're no longer segregating signaling molecules in the same way? That's really intriguing to me.
That's fantastic. Yeah, the relation to chronic pain and age-related changes, there's so much potential there. We did have a couple of questions that came in ahead of time, I'll have you know,
Okay.
people in who couldn't make it today. And one of them was about interventions, perhaps if there's ways of driving molecules through the skin into this system for distribution. And I think we're all aware of maybe how those things might happen, but maybe this is the pathway or the
Right.
mechanism underlying
Well,
that.
we know, you can have nicotine patches. You can have opiate patches. We do this already. There was a startup company that got in touch with me that had some mechanism for pushing stuff to open up the spaces in the squamous so stuff could get through more easily. And the physiology of this was a bit beyond me. It's not kind of what I do or can do. But yeah, what are the mechanisms that hold those spaces closed? What would allow different molecules to move across them? Could simply applying hyaluronidase to open up the space, would that allow molecules to get through into the interstitial spaces and then distribute? But I'm a pathologist. I don't do things like this. But these are the important questions to ask. And if we're talking about therapeutics, that reminded me of something else, which may come back to me or not.
And you might just take a look at one last question in the chat about functional implications related to the heart. And yeah, maybe you can revisit that. You sort of suggested there was some
Yeah.
further information to chat about.
So when you map mouse hearts and human hearts, we need more hearts. The interstitium of the pericardium is continuous with the interstitium through the muscular wall of the heart, is in continuity with the interstitium of the endocardium. The epicardium interstitium is continuous with the adventitia of the great vessels. So when the heart contracts during systole, blood rushes out the aorta, but the pericardium is relaxing. So fluid can flow into the pericardium from within the wall of the contracting ventricle. Now you have diastole, the heart relaxes, presses outward, compressing the space in the pericardium, and that would mean the fluid is going to go out into the adventitia. So is the heart actually pumping two fluid systems, one high volume, the blood, and one low volume, the interstitial fluid? The structures are all there. I can show you pictures of this, but functionally, and when you think about 50% of congestive heart failure in the world is diastolic heart failure. And it's often diseases that would affect the interstitium, like amyloid, for example. So I think we can make a case that there's some important physiology here that really no one has ever paid attention to.
Well, with that type of cliffhanger, I think we're at the perfect point to call it a day. It's been a wonderful hour spending our time with you, Dr. Theise. And I will suggest that you may be back, and we would love to have you back for additional topics that are just as fascinating that you've explored into the realm of complexity, areas that you've written about in your book. So I'll give you a little promo on the book there as well.
Okay, thank you. Oh, I should have put in a book slide. All right, never mind. I'm not very good at this. So.
Well, listen, if you can work in Taylor Swift somehow to it, you're going to be fine, I'm sure.
I have to get her my book is what I have to do. Patti Smith got it, and I had a big jump in sales, but never mind.
I'm so happy for you. That's great. So let's call it a day, keeping mindful of everyone's time. Thank you again to our speaker, and thank you for coming to the talk, everyone. This is the benefits of becoming a member of ForceNet. Wonderful speakers and other content like this that you'll also see appear on our YouTube site in the coming weeks, in case you have a chance to see this again or tell your colleagues about it. So enjoy the rest of your day, and thank you once again, Neil, and to all of you for attending.
Thank you, everybody.
Neil, if you just stick around for a second.
Yeah, be happy.